It's 7:43 in the morning on December 26, 2004. The beach at Yala National Park in Sri Lanka is calm. The water is warm. Tourists are setting up for a morning on the sand. And then something happens that none of the human observers understand in the moment, but that every scientist who reviews the footage afterward finds deeply unsettling. The animals leave, not in a panic, not in a stampede, deliberately, purposefully. Elephants that have been grazing near the beach turn inland and walk. Flamingos that have been nesting in low-lying wetlands lift and relocate to higher ground. Dogs in coastal villages refuse to go outside. Captive animals at a wildlife sanctuary move to the highest points of their enclosures and refuse to come down. Zoo animals retreat to their shelters and will not emerge. 45 minutes later, one of the most devastating tsunamis in recorded history kills 230,000 people across 14 countries. The animals knew. Not one wild animal was found dead in the aftermath in Yala National Park. Not one. In a disaster that killed human beings by the hundreds of thousands, the animals were already gone. This is not a fairy tale. This is documented, verified, studied by researchers from multiple institutions across multiple disciplines. And it raises a question that the survival community has almost entirely failed to engage with seriously. If animals can detect a tsunami 45 minutes before it arrives, what else can they detect? How early? And how do you read the signal? Today, we answer those questions. Because in a world where the early warning infrastructure is down, no weather alerts, no USGS notifications, no emergency broadcasts, no functioning cell towers, the animals around you are the early warning system. They've always been. We just stopped paying attention. The biology of animal early warning. Before we get into specific signals for specific disasters, you need to understand the biological mechanisms that make animal early warning possible. Because this isn't mysticism. This isn't folklore dressed up as science. There are specific, measurable, peer-reviewed physical mechanisms that explain exactly why animals detect what we can't, and understanding those mechanisms tells you which animals to watch for which threats. The first mechanism is infrasound sensitivity. Infrasound is sound below the threshold of human hearing, below 20 Hz. Humans cannot hear it. We cannot feel it at low amplitudes. To us, it doesn't exist. To a significant number of animal species, it's a rich information channel that carries signals across hundreds and sometimes thousands of kilometers. Earthquakes generate infrasound. The initial P waves of a seismic event, the compression waves that travel fastest through the Earth's crust, arrive at the surface before the destructive S waves and surface waves that cause the shaking humans feel. These P waves generate infrasound as they reach the surface. The difference in arrival time between P waves and S waves can be anywhere from a few seconds to several minutes, depending on distance from the epicenter. Animals that can detect infrasound are effectively receiving an advance warning signal that physics makes available before the destructive energy arrives. Elephants hear infrasound. They also transmit it, communicating across distances of up to 10 kilometers through vocalizations below human hearing range. They feel it through their feet. Sensitive mechanoreceptors in elephant foot pads detect ground vibration with extraordinary precision. When an elephant turns inland and walks with purpose in the 30 minutes before a seismic event, it is responding to physical signals that are genuinely present in the environment. It is not psychic. It is receiving data on a channel we don't have access to. Whales and other cetaceans use infrasound for navigation and communication across ocean basins. The fact that beached whale events sometimes precede earthquake activity in coastal regions is not coincidence. It is consistent with infrasound disruption of navigational systems. The signal that guides them is being overwhelmed or distorted by the seismic precursor activity. The second mechanism is electromagnetic field sensitivity. The Earth's magnetic field changes measurably in the days and hours before significant seismic events. This is called seismo-electromagnetic activity, and it's one of the most actively researched areas in earthquake prediction science. Piezoelectric stress in rock, the electrical charge that certain minerals generate when mechanically compressed, creates detectable changes in the local electromagnetic environment as tectonic stress builds before rupture. Many animals are magnetoreceptive. They navigate using the Earth's magnetic field. Birds use it for migration. Bees use it for hive navigation. Certain fish species use it for orientation. Sharks have specialized organs called the ampullae of Lorenzini that detect extremely subtle electromagnetic changes in seawater. When the electromagnetic environment becomes abnormal in the days before a seismic event, these animals experience the equivalent of their navigational instruments going haywire. Their behavioral response, confusion, relocation, abandonment of normal patterns, is a byproduct of that disruption. The third mechanism is chemical sensitivity. Before earthquakes, volcanic events, and certain severe weather systems, chemical changes occur in the environment that highly sensitive olfactory systems can detect. Radon gas, a naturally occurring radioactive gas produced by uranium decay in rock, releases into groundwater and atmosphere as tectonic stress fractures rock in the days before a seismic event. Dogs have olfactory systems roughly 10,000 to 100,000 times more sensitive than humans. They can detect radon concentration changes that no human-built sensor would flag as significant. Similarly, before tornadoes and severe convective storms, the atmospheric chemistry changes in ways detectable by animals with sensitive olfactory or pressure-sensing systems. Ozone concentration increases. Humidity gradients steepen sharply. Pressure drops in ways that animals with sensitive baroreceptors register well before the event is visible. Sharks detect chemical changes in water with extraordinary sensitivity. Certain fish species, catfish are perhaps the most studied, have been observed exhibiting unusual surface behavior in the days before seismic events in multiple independent studies across Japan, China, and Italy. The mechanism is likely a combination of electromagnetic sensitivity and detection of dissolved gas changes in the water column. The fourth mechanism is barometric pressure sensitivity. Many animals are exquisitely sensitive to barometric pressure changes that human bodies register only vaguely, if at all. Fish adjust their swim bladders in response to pressure. Birds have Herbst corpuscles, mechanoreceptors in their beaks, that detect pressure changes far more precisely than any human sensory system. Insects respond to pressure drops that precede severe weather systems. The behavioral implications are measurable and consistent. Fish move to deeper water before storms. Birds land in shelter before pressure systems arrive. Insect activity drops abruptly. The sudden disappearance of insects on what appears to be a normal day is one of the most reliable indicators that severe weather is incoming within hours. Now you understand the mechanisms. Now let's talk about specific signals for specific disasters, because this is where the knowledge becomes operational. Earthquakes, the signals and the timeline. The research on animal earthquake precursor behavior is the largest body of work in this field, and it comes from cultures that have been observing it systematically for centuries. Chinese earthquake researchers have been documenting animal behavior anomalies as part of their monitoring programs since the 1970s. Japanese researchers have decades of catfish behavior data correlating with seismic events. The patterns are consistent enough that multiple governments have formally studied them as early warning components. Here's what the research shows, organized by timeline. Days to weeks before a significant seismic event, the first signals appear in animals with the highest electromagnetic sensitivity. Migratory birds may alter routes or stage in unusual locations. Bee colonies have been observed abandoning hives in the days before earthquakes in historically documented cases from Italy and Japan. Certain snake species, which are sensitive to both ground vibration and electromagnetic changes, have been observed emerging from hibernation in winter conditions in the days before earthquakes in Chinese records, most famously before the 1975 Haicheng earthquake, where mass snake emergence in winter was one of several factors that prompted a successful evacuation. Hours before an event, the signals become broader and more behaviorally dramatic. Dogs refuse to go outside or become agitated without visible stimulus. Cats become hyperactive or hide. Livestock in enclosures move constantly, cannot be settled, refuse to eat. In documented cases from multiple events, zoo animals began their unusual behaviors anywhere from a few hours to several minutes before shaking was felt by humans. The most reliable short-term signal, minutes before surface wave arrival, is animal flight. Not individual animals, groups, herds, flocks, colonies moving purposefully away from the epicentral direction. This is the P-wave response. The infrasound and ground vibration from P-waves arriving at the surface before the destructive shaking is the trigger. Animals that detect it move. Direction matters. Animals tend to move away from the source, which in a real situation with multiple observations could theoretically give you directional information about where the event is centered. What you watch for in practice. Any simultaneous behavioral anomaly across multiple species with no visible stimulus. One dog barking is not a signal. Every dog in the neighborhood barking simultaneously at nothing at the same time that birds lift from trees in an uncharacteristic mass departure, at the same time that your livestock cannot be settled. That convergent multi-species behavioral anomaly is the signal. Single-species anomalies have too many alternative explanations. Multi-species simultaneous anomaly narrows the possibilities dramatically. The critical action window is whatever time you have between observation and event. Depending on your distance from the epicenter, that may be seconds or minutes. The response is not to run outside. Falling masonry kills more people in earthquakes than structural collapse in most event types. The response is door frame, interior wall, or under a heavy table. Drop, cover, hold. Every second of warning, even 10 seconds, dramatically improves survival outcomes. Tornadoes and severe weather, the signals and the timeline. Tornado animal precursor behavior is perhaps the most practically applicable signal system for most people in North America because tornado events are geographically concentrated in regions where millions of people live, and the standard warning systems, sirens, phone alerts, are only as good as the infrastructure supporting them. The timeline here is longer than earthquakes, and the mechanisms are primarily barometric and infrasonic rather than electromagnetic. The day before significant convective weather systems, the first behavioral shifts appear. Sharks in coastal waters move to deeper water as pressure drops. Multiple tagging studies have confirmed this. Birds begin feeding with unusual intensity. The hyperphagic feeding behavior that precedes weather events appears to be driven by the bird's accurate anticipation of a period during which flying and feeding will be impossible. If you observe birds feeding frantically and continuously in the morning hours of an otherwise unremarkable-looking day, check the pressure. Check the sky to the southwest if you're in tornado country. Something is building. Cows and horses lie down in numbers before pressure drops associated with incoming storms. The folk observation that has been statistically validated in multiple agricultural studies. The mechanism is likely barometric, though the specific receptor pathway is not fully confirmed. What matters for practical purposes? If your livestock or a farmer's field you can observe is showing unusual lying behavior on a clear morning, the atmosphere is doing something that their pressure sensors are registering. Insects disappear. This is perhaps the most universally applicable signal because insects are everywhere, their absence is noticeable, and the mechanism is well understood. Barometric pressure drop suppresses insect flight because their flight systems are pressure sensitive. Before a significant storm system, insect activity drops measurably, sometimes hours before the storm arrives, sometimes more than a day before. The practical observation is simple. If you step outside on what looks like a normal afternoon and it is conspicuously, unusually quiet, no bees on flowers, no flies, no beetles, the background insect hum that you usually don't consciously notice is absent, check the sky. Check the pressure if you have a barometer. Something is coming. Birds fly low before storms. This is another statistically validated folk observation. The mechanism is that low pressure reduces air density, making high-altitude flight energetically inefficient. Birds that are flying in the hours before a significant pressure drop tend to fly lower than normal. Combined with the feeding frenzy observation, low-flying birds feeding intensely is a compound signal that multiple independent variables are simultaneously pointing at incoming severe weather. For tornadoes specifically, the most important animal signal is the one that comes in the last minutes, the period when a tornado is forming or approaching but may not yet be visible. Birds go completely silent. This is the signal that appears most consistently in eyewitness accounts from people who survived tornado events, particularly people in rural areas without sirens. The normal background bird sound, which humans register subconsciously even when not paying attention to it, stops completely. The birds have detected the infrasound from the forming rotation, and they have gone quiet and still. If you are in tornado country and the birds go completely silent on a day when you have already observed other anomalies, insects absent, cattle lying down, birds flying low and feeding frantically in the morning, do not wait for the siren. Get to your shelter. The animal system just gave you warning that your infrastructure may or may not corroborate in time. Volcanic events, the signals, and the timeline. Volcanic early warning from animal behavior offers some of the longest lead times of any natural disaster precursor system, potentially days to weeks, but requires knowledge of what you're looking at because the signals are more subtle and geographically specific. The primary mechanisms are chemical, particularly radon and other volcanic gas emissions that precede eruptive activity, and infrasonic, as volcanic systems generate low-frequency sound during the pressurization periods before eruption. Weeks before significant eruptive events, groundwater chemistry changes. Animals that drink from local water sources, livestock, wildlife, may change their drinking behavior. Avoiding previously used water sources without apparent reason, drinking less. In multiple documented cases preceding volcanic events in Iceland, Japan, and Italy, livestock behavior changes at water sources were noted by farmers in the weeks before eruptions. The water was changing chemically in ways the animals detected and found aversive. Bees abandoned hives in the weeks before significant volcanic events in historically documented cases from Vesuvius area records. The electromagnetic and chemical changes associated with volcanic pressurization disrupt the navigational and communication systems that bee colonies depend on. A colony that abruptly absconds abandons a hive without apparent pathological reason, no disease, no parasites, no predator disturbance, in a volcanically active region is potentially registering pre-eruptive activity. Birds leave the immediate area of a volcano in the days before significant eruptive episodes. This has been documented before multiple events and is consistent across species. The infrasound generated by the volcanic system as pressure builds creates an environment that birds find aversive and flee from. The practical problem is that this requires baseline knowledge of normal bird populations in your area. If you don't know what normal looks like, you can't identify the departure. This brings us to a principle that applies to all animal early warning systems, but is most critical for volcanic precursors. You cannot read anomaly without baseline. The entire system depends on knowing what normal behavior looks like for the animals in your specific environment during the current season. A behavior that is anomalous in summer may be completely normal in autumn. A behavior that is normal for one species may be a red flag in another. You cannot parachute into an unfamiliar environment and read animal early warning signals reliably. You develop this capability by paying attention continuously, not in crisis, but all the time. Floods, the signals, and the timeline. Flood animal precursor behavior is perhaps the most behaviorally obvious of all the disaster categories because the signals are large, numerous, and involve species that most people interact with regularly. Earthworms surface en masse before significant rainfall events and floods. The mechanism is barometric. They detect pressure changes associated with incoming moisture systems and surface to avoid drowning in saturated soil. Mass earthworms surfacing on sidewalks, driveways, and open ground in the absence of recent rain is one of the most reliable flood precursor signals available. It is also one that most people observe without registering its significance. Ants relocate their colonies before floods with a lead time that has been measured in multiple studies at anywhere from several hours to more than a day. They move upward, to higher ground, to upper walls, to elevated surfaces. A sudden mass ant movement up walls, up tree trunks, across open ground in an uphill direction, with the urgency and organization of a colony that has decided to move rather than forage, is a flood signal. They are reading the pressure, the humidity, possibly the electromagnetic changes in the soil moisture content, and they are acting on what they read. Frogs and toads call more intensely before rain events. This is commonly known. What is less commonly known is that sudden cessation of frog calling in an area with an established frog population can indicate an incoming weather event severe enough to drive them to shelter. The normal call stops. The abnormal silence means something. Fish in rivers and streams move to deeper, slower water before flood events. Anglers who pay attention have known this for generations. The fishing goes dead before a flood because the fish have already repositioned. If you're near a river and the fishing is gone completely dead without temperature or seasonal explanation, pay attention to upstream weather. Building your animal early warning system. Now we get to the practical architecture, because knowing that animals predict disasters is interesting, but knowing how to actually use that knowledge in a preparedness context is what this channel is for. Step 1 is establishing your baseline, and it cannot be skipped. Choose the animals you have regular access to, your own pets, livestock if you have them, the birds in your yard, the insects in your garden, wildlife you encounter regularly on walks or near your property. Over weeks and months, observe their normal behavior across different weather conditions, different times of day, different seasons. This baseline is what makes anomaly visible. Without it, you're looking at a graph with no x-axis. You can't identify deviation if you don't know where normal sits. The specific baseline observations worth tracking. Where do birds normally feed and at what times? What is the normal background insect activity level in your outdoor spaces? How do your pets normally behave on different types of weather days? Do your animals have any pre-existing health issues that could confound behavioral signals? All of this is context that determines whether a behavior is a signal or noise. Step 2 is building a multi-species observation habit. Single-species anomalies are interesting. Multi-species simultaneous anomalies are actionable. Make it a habit, particularly in the early morning, which is when the most sensitive behavioral window exists for most animal species, to do a quick environmental scan. Birds normal? Insects normal? Pets normal? Livestock normal? This scan takes 30 seconds if you know what normal looks like. And in that 30 seconds, you might be doing something that no government early warning system can do for you. Integrating real-time biological data from multiple independent sensor systems simultaneously. Step 3 is cross-referencing animal signals with physical indicators. Animals are not infallible. Their behavior has many drivers: predators, disease, mating season, territorial disputes. A single animal doing something unusual has a long list of mundane explanations. The power of the animal early warning system comes from correlation. Animal anomaly plus pressure drop plus unusual cloud formation plus temperature change plus a second unrelated species showing simultaneous anomaly. Each variable you can confirm multiplies the reliability of the signal. A barometer costs almost nothing and tells you what the animals are responding to in barometric terms. A simple thermometer tells you about temperature inversions. Your own observation of cloud types, cumulonimbus anvil heads, unusual lenticular formations, wall clouds, adds the meteorological layer. When three of these systems are simultaneously pointing the same direction, you act. Step 4 is having a pre-decided response threshold. This is the step most people skip, and it's the one that costs them the most time in an actual emergency. Decide in advance. If I observe simultaneous behavioral anomaly in 3 or more species with no obvious alternative explanation, I implement my shelter plan or my evacuation plan immediately, without waiting for official confirmation. The reason you decide this in advance is that in the moment, the temptation to wait for official confirmation, to not be the person who overreacted, is enormously powerful. And waiting is exactly what kills people in fast-developing events. The Tuareg don't wait for someone to confirm that the desert is dangerous. The Inuit don't wait for a weather service to tell them the ice is wrong. They read the environment, they trust the read, and they act. That capacity for decisive action based on environmental reading is not impulsiveness. It is the product of systematic observation converted into pre-committed response protocols. The history that should have changed everything. Let's return to where we started, because there's a piece of the 2004 tsunami story that most people don't know. The Moken people, sea nomads who live on the Andaman Islands and have for centuries, lost almost no one in the tsunami. Not because they had better infrastructure, not because they had warning systems, because they had a cultural knowledge system that included reading animal and ocean behavior as early warning signals. When the sea did something unusual in the morning hours of December 26th, when the water receded in the specific way that their oral tradition said meant danger from the deep, they moved to high ground. They moved because their tradition told them what the animals and the water were saying. That tradition saved them. The oral tradition they carried was essentially a compressed, multi-generational record of animal and environmental early warning signals, encoded into story so it could survive without writing across hundreds of years. It is one of the most sophisticated, low-technology survival systems ever developed, and it worked when a modern telecommunications infrastructure failed. You can't encode centuries of observation into a tradition overnight, but you can start the observation. You can build the baseline. You can establish the habit of reading the living environment as a data source rather than as scenery. The animals have not stopped broadcasting. We just stopped listening. The grid will fail again. The cell towers will go down again. The early warning sirens will either not function or not exist in your specific location when you need them. But the birds will still be feeding at dawn. The insects will still be reading the pressure. The earthworms will still be telling you what the soil knows. The dogs will still be hearing what you can't. The question is not whether the signal is there. The question is whether you'll know it when you see it. Start watching tomorrow morning, before you check your phone, before you look at the news. Step outside and read what's there. The most sophisticated early warning system on the planet has been running continuously for 500 million years. It's free. It requires no batteries. It cannot be hacked or jammed or shut down by a government or a solar flare or a failing power grid. It just requires you to pay attention. Start now, before you need it.